comparative test on the gravity of electrons and positrons via horizontal supercooled vacuum tube.
A technician, and I did my PhD on neutron reflectometry, and with this instrument it was also possible to measure the gravitational fall of a neutron. So that's why I became interested in gravitation on elementary particles. I must thank the organization for having me here, and especially the Santilli Foundation for the support.
Absolutely, because I don't see the reason why. Thank you.
Talk about the principle of the experiment, then the requirements, the technical requirements for this instrument, and then I will present the conclusions. This is one of the social implications that the theory might have. Here I come from Holland, and we are used to using renewable energies, as you can see from very old. These are the windmills, which were used to pump out the water against gravity up in the canals to let it flow away. Because as you know, Holland is below the sea level. But anyhow, we can define two particles. I represent this as apples because of our Newton gravity was found, as the history claims, by dropping an apple which Newton saw. But anyhow, let's say we have a positron and we have an electron. And what could happen to those things? They could both fall down, or they could both fall up. But there's also a possibility, of course, that this would happen, or this. You could say, why are you claiming that the electron is falling up? It's normal matter, so it should fall down. But actually, the experiment on gravity on the electron was performed, but didn't give good results. So it is not clear. It has never been measured, the gravity on an electron, neither the gravity on a positron. A little bit about the history of the electron. It was only experimentally detected at the very last part of the 19th century. Of course, it was a hypothesis long before and during the completed, well, you could say about electricity theory, but it was only discovered by Thomson in this year. By now, the mass has been measured and the electric charge with very high accuracy. And in most experiments, mostly the ratio between the electric charge and the mass is measured. But for an electron, there is also a possibility to measure the charge independently. The magnetic moment of an electron is very important for its structure. Was found out in 1970 by H. The weight, although there has been an experiment, but it has never been determined with accuracy. For the positron, the story is less old, but not so much less, you could say. It was experimentally detected in 1932. And for the positron, only the mass divided by charge. So the ratio has been determined, not the charge separately or the mass separately. And the weight, nobody knows. The experiment which did measure or tried to measure the weight of an electron was performed by Witteborn and Verba way back in 1967. They used this experiment, which is mainly vacuum tube, which is positioned vertically and consists of some drift chambers. These drift chambers contain a very low potential, and what happens is the following. We have the electron at the source position. The source is here down, and what they did is they let the electron move up first fast, then this is a drift tube where it moves very slowly, and then it is accelerated again by some potential and hits the detector at the top of the screen. And what they did is they measured the time of flight. So they knew when the electron was emitted here, and they measured the time it took the electron to reach the top. And of course, this time of flight depends on the velocity of the electron, the initial velocity. If the faster the electron moves, the sooner it will be hit at the detector. And here you can see the time of flight as a function of the initial velocity of the electron. As you can see, when the electron is moving very fast, the time of flight is very short, and the slower the initial velocity is, it takes much longer time for the electron to reach it. And even so, if you draw up an apple, it has a maximum height, of course. And if its maximum height is less than the drift range where the electron is moving for the most time, then the electron cannot reach that point and will drop down again. So what they theoretically estimate is that there is some maximum time of flight for the electron, and afterwards, when the electron is lower, they will not detect any electrons anymore. So the purpose was to measure this maximum time, and that would give the weight of the electron, because the electron is pulled back by this weight, and this will reduce this velocity. So this was the principle of the experiment. Just release a lot of electrons with different energies, measure the time of flight, and find out the maximum time of flight. And if this maximum for normal gravity on an electron, this maximum will be at this point for this velocity and this time of flight. And here you can already see the problem which they have. This initial velocity of the electron corresponds to kinetic energy of 51 picoelectron volt, which is very, very small. So this Wittenborn and Fairbank experiment, the initial intention was that they also do it with positrons, and I don't know why they didn't. Maybe they were dissatisfied with the experiment, or they never repeated the experiment with positrons. Then the interest switched to antiprotons, or to protons, because the mass of the proton is about 1836 times heavier than the electron, and the kinetic energy of these protons is also for the same amount larger, which would be easier, they imagined. So the focus was going to the antiproton experiment on that, and there has been an experiment at CERN between 1982 and 1996, which prepared such a thing at the Lear facility. But the problem they have is that they create normally protons with antiprotons with enormous energy, and this energy has to be reduced to the nanoelectron volt level, which is very, very hard. So they came a long way, but I have not seen a report from CERN where they actually did measure the weight of the antiproton. And currently there are two experiments at CERN which independently try to measure the weight of anti-hydrogen. And why are they using anti-hydrogen? Because it's neutral. And when it's neutral, they don't have to care so much about electric or magnetic fields. That's experimental advantage. Another experiment is proposed at the Fermilab to measure the weight of anti-hydrogen, but these efforts are ongoing, are on the way, but They're all based on neutron particles. And of course, a neutron particle is bound of two charges, of a positron and an antiproton, and its bound energy is also included in the system. So Professor Santilli's claim is that it could be that the neutral antimatter has a different weight as just the sum of the two elements constituting the antimatter. So it's actually a different experiment. So why was the switch from charged antimatter to neutral antimatter? So why not using any more antiprotons or positrons? Well, of course, a positron and an antiproton has a charge, and the charges they are attracted by electrical forces or repelled by electrical forces, and there can be electrical forces from all kinds of contributions. And the most important one is the surface potential. I will elaborate it on later a bit more. The second one is that the gravity of the electrons in the tube, in the shielding tube, there are also electrons, and those electrons are pulled also down, and they might give an electric force counteracting the weight of the electrons. But of course, because we propose to do the electron and positron test together, this is of no interest anymore for us. Well, you have to shield very good the electrical forces, and you can have leaking in the tube because it's never possible to stop an electric field at a certain position. It's also always bulging in or bulging out. And if you have a small tube, this is a big problem. But our proposal is for a very long tube, and then this problem is very much reduced also. And you can have a possible off-axis movement. The charged particle is moving in a shielded conducting tube, and then you have the mirror charge moving along in the shielding, you could say, and the electric field of the electron is pulled to be perpendicular to the surface of this conducting tube, and then you have an image charge moving along with your electron or with your positron. The image charge, if you have your electron exactly at the axis of the tube, has zero force on your electron. So this means that you cannot go too far off axis, and this also means that you should use a big diameter tube and not a small one. Of course, you have also forces due to due to magnetic fields. You have the scattering of the residual gas atoms, and you have, which is a very problematic thing, is that you have a low yield also for microelectron positrons. And for the Wittenborg-Fairborn, you needed positrons or electrons with an energy of 51 picoelectron volts, which is about, compared to microvolts, a factor of 10,000 even lower. So this is a real problem, the source intensity of the positrons or the electrons. And why also there was a question about the usefulness of the precision of the experiment of the experiment at Leer. They said we can measure maybe between 1% and 0.1%, and they said that could be a problem because then we cannot check the asymmetries, etc. But if the question is falls it up or falls it down, this is more than sufficient accuracy. So this is not a problem for us. Most objections which we stated last can be overcome by using a horizontal vacuum well-shielded flight path. So we are not going to send the electron upwards or the positron, but just let it move horizontal. And this is the principle of the experiment. We take a very long vacuum tube with a length L, and we put the source at the start of the tube and a detector, position sensitive detector at the other side. And what we do at 0 time, we release an electron at the source position. And then when the electron moves very fast, it has no time to drop down or to fall up, and it will hit the detector at this position. When the electron moves a little bit slower, then it has time to drop off, and it moves. Let's assume for now that the electron has normal gravity, and then it will enter there. And of course, the slower the electron will go, the lower it will hit the detector. So by just measuring the position of the electron on the detector, we have the trajectory of the electron, and we know that it has fallen down or up. The same can be done for the positron. If it goes fast, it ends up in the middle of the detector, and if it goes slower, then it falls up. In this case, let's assume it falls up, then it comes here. The difference is given by the gravitational constant, and of course it's just a trajectory, a parabola, which increases with the square of the time of flight. Let's make it a little bit more complicated, of course, because what we have is not a horizontal electron beam, but we have a point source. And what we're going to do, we're going to project the point source at the detector position by means of a lens. It is an electrostatic or electromagnetic lens, which is able to focus all electrons coming from this point on a point on the detector. What happens is that, if the electron has now different trajectories, they still focus on the same point. And of course, the focusing is at a different point for different energies or different gravitation constants. Here you can see how big is the deflection as function of the kinetic energy of the positron or electron. We have here a micro electron volt scale, and we have here the deflection in millimeters. So if you want to have an appreciable deflection, about in this ratio, between 10 millimeters and 1 millimeter, which you can clearly see with your eye, then you should have a kinetic energy depending on the length of the flight path. So the smaller the length is, the smaller the kinetic energy is you will need. But you can see here the energy range which you need for a deflection, for instance, of 10 millimeters and a flight tube of 100 meters. The energy you need is 20 micro electron volt. It's much larger. So this means that the problem of the source of the energy distribution of the positron of the source is no issue anymore. Okay, of course, an electron it's a wave packet, and this wave packet has a wavelength, the Broglie wavelength, which is defined like this. It's inversely proportional to the velocity. So the longer or the smaller the velocity of the electron, the longer the wave of the electron is. And typical value for the electron is that if this electron moves with a velocity of 7 kilometers per second, then the wavelength is 100 nanometers. So it's typical. And you can see here, you can calculate the actual wavelength from the velocity by this formula, which contains the inertial mass of the electron. Because of the wavelength properties, you cannot image the point source as a point on the detector screen, but you image interference pattern, which is known as the Airy pattern, and the main intensity of the electrons will end up here, but there are some neutrons or electrons will go in different positions, although the system is perfectly focused. Of course, we need to be able to discriminate where the position of the electron or positron is. So this point, this source or this diameter must be smaller than the deflection we want to measure. So the diameter is known as the area disk, and it is related to the wavelength and the length of the image, the distance of the source in the image, and the aperture. The aperture of the lens. So if you fill that in, if you say the area disk must be larger than the deflection or smaller than the deflection, so that we can have a good discrimination, and it means this is the first criterion we have. The time of flight must be a lot larger than this value. You can see here. This is the electron properties. This is the aperture of the lensing system, and this is the gravitational constant. And you can rewrite this by taking these values, and typical, if you have an aperture of 10 centimeters, so you have the electron beam is 10 centimeters in diameter, then this T0 is 1.8 milliseconds. So that means that the minimum time of flight will be this value. So this is the first criterion you can use to design your experiment. Normally, of course, the electron source or positron source, they'll have a limited size. It cannot be zero size, the source. And if you take this size as a limiting factor of your experiment, then you will see that the aperture is coupled to this resolution. This is a very simple equation which you again can use to design your experiment. This is the resolution of your source. So if you have a source of 100 micrometers, then you can directly see, depending on the gravitational constant, what is the optimal aperture of the system. If we define the ratio between the aperture and the length of the flight tube by eta, this is the ratio, then this ratio must have got, it has limits. It cannot be too large, because then you cannot focus your system very good. It cannot be too small, then your source intensity will never be high enough. So this eta will be somewhere between 1,000 and 1/10, for instance. And here you can see the requirements for the flight paths you will need, depending on this eta function and on the resolution of the source of your complete system. So if your flight path can come up from 1 kilometer down to 1 meter, but the optimal position will be somewhere here. Because the resolution of your source, well, if the source is too small, then you have no intensity left, and too large is not necessary. So your resolution of your source will be somewhere here. And this, you can say the kinetic energy of the source particles. You can have the same arguments. The kinetic energy for some resolution must also be here. This limits the size and the requirements of your instrument to these regions. These are the interesting regions experimentally seen, which are experimentally possible. Some word about the most problematic thing is the patch effect. If you look at a metal surface and you polish it or you don't polish it, but then you will see all kinds of domains. Domains depend on how your metal is prepared, but the size order is 1 micrometer. And those domains all have different orientations, and because they have different orientations, they have also different electric fields and potentials. And of course, the gravity on an positron is very small. You could, if Professor Santilli would have one positron and in his hand, and I have one positron in my hand, then they are repelled by the force. When we are at a distance, the Coulomb force is equally strong on 5 meters as the gravitational force of the Earth to the positron. So only two positrons on a distance of 5 meters give the same force as the gravitational force we are trying to measure. So that's a really tiny force. So you must be extremely careful that we shield all electrical or magnetic fields. And the shielding can be done very well by means of superconducting materials. but also superconducting materials might have some kind of patch effect on the surface. To get an estimate for how important is this patch effect for the experiment, we will use optical phase analogy. Optical phase of a system is just you could say the phase acquires along a path from this is the refractive index, and when you take when you divide it by the wavelength here, you get the optical phase of which the particle or the photon acquires along this path. We apply it here for the positron or the electron, and the refractive index of a particle can be calculated depending on the potential in which the particle is. This is given by this relationship. Where you can see this is the electric elementary charge, the mass of the particle, the Planck constant, and the wavelength of the particle squared, and this is the potential. So this is the refractive index which we can use to calculate the optical phase of the particle. And for a good instrument, the optical phase for all the different parts the particle can take must be very much smaller than 1, because then all the particles are in phase, and you get the simple area focusing. And if you assume that the surface patch effect is Gaussian distributed with some potential, Gaussian potential, and domain size, zeta, then this will be the optical phase acquired along the flight paths of the instrument. And you can see it is given by the wave, it's proportional to the wavelength, inversely proportional to the aperture of the system, and here this is the length and the patch, the size of the patch domains. And this is a constant depending on the particle. It's given here, it's very small, 1.5 times 10 to the minus 11 volt-meter. It means that this product must be of this order. There is a reduction factor here still, so not of this order, but this is 1 micrometer over almost 10 centimeters, so this is one factor of 100. So we have to be in the region of 1.5 times 10 to the minus 9 centimeters. So this is the requirement to get an optical phase of the particle, so that this patch effect doesn't disturb the experiment too much. And well, you can reduce this by reducing the crystalline size, of course. So it's very important to have material with very small crystallites, and by reducing the patch effect. As an example, for the vertical flight paths used in the Wittenborn-Fermat experiment, they had the patch size of about a micrometer, and then to have a neglectable influence, the patch voltage has to be below 250 nanovolts, which is very difficult. In the experiment with Fermat, they said by reducing the temperature to below 4.5 Kelvin, they reached the fact that it was less than 250 nanometers. But if you have a horizontal flight tube, then and the same patch size, then the patch effect has only be below 100 to 10 micrometers. It means increase of a factor of 400. So our experimental problems with the patch effect are a factor of 400 less than used by Wittenborn and Fermat. An interesting addendum to this is that if you fill in the deflection of the particle, then this will be the optical phase acquired. And you can see this is completely independent of the mass of the particle. It means that it has no advantage to do this experiment with protons or antiprotons instead of positrons. So we don't have to go to CERN. We can use any positron source, and the positron source is readily available. Actually, you can take a radioactive source, like a 22 natrium source. You can also go to a reactor. In Delft, in Holland, they have the most powerful positron source in the world. So that would be a good candidate for that. But this, I want to stress this. This means that the reason why CERN took over the experiment, you could say, is not a valid reason in this case for a horizontal flight class. Because it doesn't matter if you use positrons or positrons, considering the patch effect, which is the most limiting effect in the experiment. So the conclusions are that with the current technology, which is of course much better than in 1967, it's perfectly feasible to do this experiment. You must be the largest challenge is that you have a good shielding, of course, and the shielding that is the most important thing, including a large flight path, of course. And another important conclusion is that for this horizontal experiment, the influence of the patch effect is much less than in the vertical experiment which have been done before. Which also holds for some most of the other reasons. So I would like to thank you for your attention.
Okay, let us thank
Yes, thank you for the beautiful action of the experiment. I have a few comments that I would like to pass to you because what is at stake is substantial. Thank you for recalling the Fairbank experiment. Let's say explicitly what is well known in the scientific community. As soon as they started their experiment in '67, there were several papers predicting anti-gravity for the process. As soon as those papers appeared in print, Fairbanks was prohibited to do the test with the positive. It is well known. But it has to be denounced openly, because otherwise we turn science into a mockery. So, because that has been going on, because the experiment with the horizontal tube has been proposed everywhere, rejected everywhere. Now, in particular, has been proposed by many physicists to CERN. There are things they have to know. Otherwise, you don't know the reality of what I call this $1 trillion trade we call physics. It's a total unregulated trade. That now is primarily dominated by politics, unfortunately. So we have to defend ourselves from this, if we care about science and society. So what happened at CERN? CERN, of course, they had alternative many different experiments to test and data. Why? They rejected the experiments with the horizontal tube, which, as you know, is resolutory. It's been stated by Professor Mills, experimentalist, by Professor Dehaene, many other physicists. It's resolutory. You will see, with sufficiently low kinetic energy of the electron, you will see the displacement with your naked eye. With your naked eye. So it is a resolutory experiment with historical proportion. Why CERN, for God's sake, has rejected this and has selected an experiment with neutral particles? Because of politics, ladies and gentlemen. Because once you do it with neutral particles, you can manipulate it. Imagine only that the neutral has to be manipulated, has to be contained in anti-hydrogen atom, has to be contained in a magnetic field, which is matter. And so therefore, ladies and gentlemen, the easiest things to manipulate in science are experiments. And I've seen so many manipulations of adapting nature to. So that in any case, I have to denounce of preferring an ambiguous experiment against a resolutory, rejecting a resolutory experiment. The only plausible or credible interpretation is that this is politics. There are many reasons why I want to warn you about testing anti-gravity, because the implications for mankind are big. That's why I'm so emotional, and I apologize for my emotion, but I care. And I'm not expecting you to agree with me, please, I beg you. No, I just want to I thank you for tolerating me. But there are many reasons for them. You just heard about the evidence that we have now, that when you have an antimatter body immersed in a matter field, the time acquires the time of the environment. So there are all sorts of, besides experimental setup, it's extremely easy to manipulate the field containing the neutral, the anti-hydrogen atom and have any desired result. Of course, the desired result we have to be compatible with Einstein relativity, which means No. Why there is such a horrendous objection against measuring the gravity of antiparticle? Because if the anti-gravity is established, this literally means that Einstein theory only apply for half of the universe. Rather now they are believing to apply for all of the universe until the end of time. So that is the origin of the opposition. In any way, after so many years of obstruction against the conduction of serious experiments at the highest American and European laboratory, I want to be on record on this conference that I have used all my energies and all my support to propose this fundamental experiment to beautiful and magnificent China. Because then in this way, basically, because certainly we cannot stop the pursuit of fundamental human knowledge just to serve the equivocal interest on Einstein. This case is unacceptable. But there is another comment I have to make. The intelligence of those people who have opposed human knowledge is skin deep. Is skin deep, because when you oppose advancement in human knowledge, you pass the scientific priority to others. My God, it's suicide. Because you cannot stop. They dream of stopping, stopping mankind from advancing, But this is very. But first of all, what they've done, they've cut themselves out. They've cut themselves out from scientific and passing scientific priority to others. But there's something much more serious. And essentially, now we're talking about passing the torch of taking America and Europe out of fundamental advancing and passing to China. If this is happened, again, I will be very happy because America and Europe deserve it. Then perfect. That's what I want to say.
Okay, great.
My wife the picture.